I just have to try to press the button saying that can be recorded. Oh, hold on a second. Sorry, because it's recording, I can't press any buttons anymore. That's very strange. Maybe if we do this. Okay. Okay, sorry about that. Okay, yeah, so it's a pleasure to be here, and yeah, it's great to hear that people are using the results from our work. I'll just start by emphasizing that the LOFAR 2-metre sky survey is one of the biggest LOFAR projects. I think it's accumulated the most LOFAR data out of any project so far by quite a long way. And it's the efforts of a large group of people. We've got about 300 people who contribute either technically to the project, or most people contribute by doing the science and yeah. Okay, so what is LOFAR? So LOFAR consists of two types of antenna. One is the LOFAR LBA antennas, and this is a picture of the LBA antennas. This actually looks much nicer than they do in real life. They're normally surrounded by lots and lots of grass and weeds growing through the racks at the bottom. But I think this one's been newly installed, and it looks really nice. These observe from about 15 to 75 megahertz, and using these dipoles, you can observe basically anywhere on the sky, and you can spread 96 megahertz of bandwidth across the sky. So if you wanted to, you could observe, for example, the whole sky just with a tiny bit of bandwidth on each part of the sky. The frequency response of the LOFAR LBAs is really, really peaky, and it's about 60 megahertz that the LBAs peak. Now, I'm not going to talk more about the LBAs, but just for completeness, I thought I'd introduce them. And there are LOFAR LBA surveys that are ongoing and actually have accumulated a large amount of data that maybe someone will tell you about in the future. But yeah, so I'm focusing more on the LOFAR HBA. So this is the high band antennas from LOFAR. And it looks like in the bottom right panel is what one of the stations look like. This is one of the international stations. So it's a very large LOFAR station. And it in this tarpaulin is basically this structure in the top right. So it's a very elaborate bit of polystyrene with a bow tie antenna in the center that's held up by the polystyrene. But amazingly, this type of structure has survived in the fields for about 15 years already. So they're really working quite well. It produces a much more constant response as a function of frequency. So you can observe basically from 120 to 170 megahertz quite easily and get nearly constant sensitivity across the band. But above about 170 megahertz, there's lots and lots of radio frequency interference. And there are windows you can observe right up to 240 megahertz. But yeah, you have to be aware of the interference. Unlike the LOFAR LBA, the HBA is limited to where it can put on its bandwidth. So you can still observe 96 megahertz bandwidth at the same time, but it has to be observed close together in the sky. So you can't, for example, map the entire sky in one observation. And that's because it's got a beamformer that is analog, and you can only form within some beam. So LOFAR is a really big telescope now. This shows the full LOFAR International Array, and it now spans nearly 2,000 kilometers. And I think there's stations in 14 different countries. So the LOFAR 2-metre sky survey collects data with the entire LOFAR telescope, and that means we've got absolutely huge amounts of data. Because we have to store a very high time and frequency resolution in order to make use of the full international telescope. But the first thing we do for standard LOTS processing is we actually remove all of the international stations, unfortunately. And I'll talk a little bit about this later. But yeah, we remove them all, and this leaves us with a resolution of about 6 arcseconds from just the Dutch stations. So in a typical 8-hour observing run for LOTSS, we're able to span about 13 square degrees of the sky. We observe 2 pointings simultaneously with about 50 megahertz of data. We reach about 100 microjanskis per beam sensitivity. And generally we image at 6 arcsecond resolution, which is just the Dutch stations. But if you include all of the international stations, you can image at 0.3 arcsecond resolution. Just this one 8-hour observing session will give you about 10 terabytes of data to process through. And processing the data is very time consuming. So if you want to just create an image at 6 arcsecond resolution, it takes about 20,000 core hours. If you want to make one at about 0.3 arcsecond resolution, you're looking at several 100,000 core hours for a single image. So LOTS is trying to utilize these capabilities of LOFAR to provide a survey that's incredibly sensitive. So competitive with something like EMU at 1.4 gigahertz. To typical radio emission. And it's going to cover the entire Northern Hemisphere in due course. We've had several data releases already from back in 2017, where we didn't really know how to calibrate the data fully, to our latest one in 2022, where we released about 20% of the map, and we really understood much better how to calibrate the data, although some improvements can be made. As you can see from this plot, LOTS is trying to push about a factor of 10 in sensitivity compared to existing surveys. And at its frequency range, also about a factor of 10 in resolution. There's also the low frequency counterpart to LOTS called LOLS, and this doesn't reach comparable sensitivity, but it's still incredibly useful for characterizing the spectrum of the sources that are detected. We have a lot of people in our collaboration, so we've got quite well, not too much organization, but a bit of organization in that we have distinct science working groups, and each science working group is led by an expert in the field. And if, for example, you want to do a project, you propose it to the science working group leader, and they check whether your project is being done by someone else, and otherwise you can go ahead and do your project. So it's not too arduous a process to go through. We have several technical working groups to try to address different aspects of the survey. 2 I'll highlight are the LOFAR International Station-based imaging. This is really an avenue that is expanding rapidly. So a lot of people working on this. I think we've probably got about 20 to 30 people working on how to exploit the international stations. And next is the WEAVE LOFAR telescope, which I'll mention a little bit later. This uses the WEAVE telescope to follow up about 1 million LOFAR sources and get their spectra. Our data are we try to release the data publicly when we're able to, so like in our previous data releases, but we obviously have vast amounts of data that are still not released. And I'll give kind of some timelines for this later, but we do have lots of data sharing agreements with individuals and big collaborations. So if you are interested in using the data, that's not public for your particular project, you can just get in touch with us and we can see what's possible. So just a little bit about LOFAR data processing. So LOFAR data processing is quite horrible in that you just have to do a lot of it. We basically have coded everything up into these large pipelines, which is nice in that you run them, you just press enter and the pipeline runs and gives you your final science products. But it's not nice in that the data is so manipulated, and actually learning how to do the process yourself can sometimes be a bit complicated because you kind of learn how to do the pipeline rather than maybe learn how the interferometer actually works. But this has kind of been necessary in order to get the science out of LOFAR, just because You have to do direction-dependent calibration, which I'll talk a little bit about later. And the processing we use for the LoTSS survey is basically described in these papers on the right by RATeS, who developed a lot of the software that we use. Yeah, so this is just showing kind of a little bit of how LOFAR data looks. So this is, for example, a famous one. It's an image of a famous galaxy cluster called the Sausage Cluster. And this is how the data looks when we observe it with LOFAR. And this is, I say it's uncalibrated, but it is actually a little bit calibrated. And you can see here that the emission is completely dominated by emission from Cassiopeia A and Cygnus A and many other sources within the field that really ruin the signal of your cluster. And this takes a lot of kind of compute and fiddling around to sort this out. For example, you have to model very carefully Cas and Cygnus A. You have to be able to remove these things from the field. And then eventually, after lots and lots of processing, you can produce from this same data set an image like in the bottom right. And that would take you about 20,000 hours to do it. And if you wanted to take it to an image like in the bottom left, where you can see the same, well, where you can see structures in the field at very high resolution, yeah, that's a few 100,000 more core hours. So how do we do LOTS processing specifically? LOTS processing is all at 6 arcsecond resolution. And basically, all we do is do a direction-dependent self-calibration. So obviously, the main thing that makes the calibration difficult for LOFAR is that across your field of view for the LOFAR HBAs, for example, you have about you have lots and lots of different ionospheres that you're looking through. So we typically calibrate in about 50 different directions for a single observation. So this means what we do, and there's also the other problem is you don't have necessarily a very good low frequency sky model of the field that you're imaging. So what we have to do is build up the sky model as well as calibrate the data in many different directions. So we use the DD Facet and KILMS from RATeS, but also Onyx Smirnov, and it's maintained in South Africa as well now, to produce these images. And they basically produce a very large image of the sky, about 8 by 8 degrees. We then split that into 45 different directions, all done within the software. You don't actually go and do anything manually. And for each of those, KILMS derives calibration solutions. We do a little bit of manipulation of the calibration solutions, like smoothing them and fitting functions to them. But essentially, then you just apply the calibration solution as an image and keep doing that several times as you improve your sky model of the region. Yeah, and then your image goes from something like this to something like this. But actually, the improvement's much more dramatic than is shown there. To give an overview of kind of the amount of data and things that we've had to plow through with LOFAR for LOTS. So far we've observed about 15,000 hours of telescope time. We've got this data from 102 different telescope proposals over the last 11 years. The survey isn't quite complete. We need about another 2,500 hours to complete it. So far in the archives, we've got about 20 petabytes of data. So it costs hundreds of thousands of euros to someone every year to store these data. And these data are split between about 3 million files and 3 different LOFAR archive locations. From this data, we actually have this LOTS sky is covered in about 3,200 pointings, separate pointings. And so far, we've processed about 2,000 of these. And we've detected probably about 10 to 15 million sources so far. And we have about 2 petabytes of final data products so far, which is, I'll tell you what these are in a little bit more detail, that we're trying to host somewhere for release. But it's obviously quite expensive to host this much data publicly. So we're trying to figure out how to do this. So we try to produce lots and lots of different products to allow for different science aims to use the data. For example, we produce just regular 6 arcsecond resolution images. We also produce images at 20 arcsecond resolution that are have a better surface brightness sensitivity. We also produce Q and U polarization cubes at a couple of different resolutions. We try to cross-match all of our catalogs. We produce catalogs, and then we try to cross-match them to produce multi-wavelength catalogs, so you can see stuff about what the radio sources that are detected are. And this has been a huge effort actually to cross-match the more extended and complicated sources. And we are able to also derive the time and frequency dependence of emission for the different sources. And finally, we keep all of the calibrated data from just the Dutch baseline, so just the 6 arcsecond resolution data. And this isn't too big. It's like a total size, yeah, of about 1.5 petabytes, I guess, for the whole 3,000 observations. And it allows you to post-process the data in whatever way you want to do it later. So, for example, you could image at higher resolution, or you could tailor your imaging to match, say, a GMRT observation or something like that for spectral studies. Yeah, and that would just be a single command of ddfacet to do that. What we've mainly used this data for so far has been to study the time dependence and things, but also to tune the parameters of calibration for a particular target. So say for example, in the bottom left here, there's an image of a galaxy cluster. And this is a really wide field image. It's 8 by 8 degrees, and it's got the little galaxy cluster you want to study somewhere in the field. And the calibration, of course, isn't tuned to that galaxy cluster. It's kind of tuned for an average over the whole field. So what we're able to do is go back into the data, remove all of the sources away from your target of interest, and then calibrate just in that direction. And then you can produce a data set that's just a few gigabytes. It can be imaged on your laptop, and it contains the full LoTSS depth stuff for a particular object. And that's something you can do with all of the data that's public. So you can do it with and it's quite easy to run. There's all pipelines for it all. So what have we released so far? So here in kind of the greeny color scale is our total observations. It's a little bit out of date actually, but it's not so far out of date. Where the color scale shows the sensitivity, and it accounts for things like the elevation of the observations, which is a big factor in LOFAR observing. The yellow region is what we released in our LoTSS DR1, and the black region is what we released in LoTSS DR2. LoTSS DR2 covers about 23% of the sky, or 26% of the sky, and detects about 4.5 million radio sources. This is where our processing is up to basically now. So far we've observed 85% of the sky. We've done about 2,700 of the 3,200 pointings. But we've had to stop observing because LOFAR has closed down for about 1.5 years whilst it gets upgraded, and I'll talk a little bit about that later. We're almost there with processing all of the data, but I think it will probably take us to the end of this year to finish processing all the data. And it's processed essentially using the same strategy as LoTSS DR2. There's been a few minor tweaks, but processing basically through the same strategy. And our ambition is to release everything that's observed. So even if it's not in a contiguous sky area or something, we're just going to try to release everything. And our timeline for this, we'll finish processing at the end of the year, and then it'll probably take about 6 months to get it all published. So probably around mid next year. And most of the sky will be released. The bit that's missing is kind of the intermediate galactic latitude area, like galactic latitude 10 to 30 or something is mainly the missing bit, or 10 to 20 or something. This is just a few of our existing images. It's always a bit hard to show the images. But this is where we're at to date. With these are all our full science ready final products. Obviously, we've got to go through and kind of identify ones where the processing's failed for some reason and see if we can try to fix it. Just to zoom in, showing what a typical area of the sky looks like. This is something that we haven't had in previous LOTS data releases. At the bottom, this is the kind of most hectic part of the galaxy in the Northern Hemisphere. And at the top is kind of a more calm part of the galaxy. And this will all be included in the data release. So as I said, we haven't really managed to change that much in the processing compared to LOTS DR2. So if you want to kind of see what the quality will be like, it's going to be very similar to that. And that's partly because there wasn't a lot of room for improvements. Maybe I'll try to show that in a bit. But also because we'd already processed so much data, we wanted to kind of reuse what we'd done largely. And not redo those things. So, for example, LOTS DR2 was 800 odd fields. So it's about a quarter or about a third of LOTS DR3. So we didn't want to do all of that processing again, really. There are a few things we have worked on, like we worked on improving the calibration in places where it clearly failed. We've worked a bit on, well, we've obtained extra observing time for low declination fields, so we get a bit more uniform sensitivity. And I'll discuss these in more detail, I think. So, for example, we have improved the cataloging in LOTS DR3. This is done. What do I want to say here? So this is a LOTS image in the top left, and this is the PyBDSF. In green are the PyBDSF sources that are found, and basically in the bottom left one is the residual image after PyBDSF. And it's a bit hard to tell here, but basically really diffuse structures are sometimes not fit so well. And also if the source density is really high, the background noise is overestimated a bit and you miss a lot of sources that you probably should detect. So we've refined our source finding approach by doing basically multiple passes of the source finding algorithm to try to detect fainter sources and pick up the more diffuse sources. And this can dramatically increase the number of sources in our catalog. For example, if you go from a 5 sigma threshold to a 4 sigma threshold using this new approach, you get about 30% more sources, but you also get you get more artificial sources. So we're trying to find the balance where the appropriate to release in terms of our catalog and what reliability. Another issue that we had with that we just generally have really is to say this is a source on the left is not a particularly complicated source, and this is what PyBDSF models it as. So you can see that PyBDSF obviously doesn't know that this is a single radio galaxy here. So we had to go through like a LOFAR galaxy zoo type process where we get lots and lots of volunteers. I think we got over 1 million clicks from people where people actually manually put together these PyBDSF components and identify the optical cross-match. And this allows us to do the cross-matching of the sources. Obviously, the simple sources we do on a computer, but these ones, these more extended ones, the best approach we have is doing it by eye. And hopefully this changes, but it's hard. Another aspect of the survey that we'd like to improve, but it's very difficult, is that because LOTS is produced from lots and lots of mosaics, many of the sources in the catalog are not deconvolved at all. This plot here just shows that basically 80% or something, or 38% of sources are not deconvolved at all in the images that you get. And this has issues, for example, if you want to measure the size of the source or its morphology or something, it's just a bit annoying that they've still got the dirty beam in there. But to do this properly, the only way we can do it is by imaging all of the pointings next to each other together. And then we can obviously deconvolve much deeper. but this is quite computationally expensive for us to do this. Another more subtle issue with deconvolution, which this one's maybe not the nicest plot in the world, but hopefully it kind of makes a point, is that the LOFAR PSF is in the top right image of this figure. You see the red curve. That's the shape of the LOFAR PSF in the LoTSS images. Now the Gaussian that's fit to it is this gray curve. So you can see obviously there's a big difference in the PSF shape between the gray curve and the red and the restoring beam. So the restoring beam is the gray and the PSF is the red. And what this means is if you inject, like for example, a Gaussian signal into your image and you don't do any deconvolution, you recover these gray points here. So that's the flux density you recover as a function of distance from where you injected the Gaussian. And ignore the difference between the blue, red, and the green, but basically maybe just take the blue, for example. This is what you recover. This is what the actual injected signal is. So it's quite different to what you'd recover in a dirty image. Now, if you deconvolve fully, then you can recover again that the shape of the blue curve, so the actual emission. But the problem is obviously that a lot of very diffuse emission in LoTSS is detected at low significance, so won't be deconvolved. So the flux densities will be hugely incorrect. There's ways you can check it, of course. So we release all of the residual images, so you can see how much this might affect your objects, for example. Here's a galactic region, and you can see that for the brighter regions of diffuse emission, you can see in the residual image in the left that it's largely deconvolved. But for this very diffuse structure in the center, you can see that in regions of that, it's not deconvolved very well at all. And the flux densities in those regions will be different because it's the dirty beam rather than the restored beam. So these are kind of just complications that are hard to rectify. Yeah, another thing I mentioned earlier is that we are trying to improve the sensitivity at low declination by spending more observing time below declination 20. We do 12 hours per pointing instead of 8. And this is simply because if your object is at low declination, then the projected area of a LOFAR station is smaller, so you don't have as much collecting area and you don't have as much sensitivity. This is showing in the bottom left, this shows our LoTSS DR2 sensitivity as a function of elevation. Elevation, you can swap declination there and it's very comparable because we obviously observe optimal elevations for our targets. But when we get down to, say, declination 0, we're really hitting about 250 microtransfers per beam noise in 8 hours, whereas at optimal elevations, we'd be more like 70, 80 microtransfers per beam. And obviously, not only does the projection of the dipoles make a difference, but the ionosphere becomes thicker when you look through more of it, so it can be harder to calibrate. Yeah, maybe I'll skip this, but basically there's other ways you can change well, maybe I'll mention it briefly. So there's other ways we can change the sensitivity that we're looking at doing in the future, but it's difficult, is that this is a LOFAR station. So on the left here is a core station, on the right is a remote station. And basically when we do the LoTSS observations, we make the remote station so it looks like a LOFAR core station. So basically we throw away half the collecting area of every remote station and we just don't use it at all. And this makes the data much easier to work with, but it obviously has a big impact on your sensitivity because you're losing a lot of collecting area. And this is something we're going to try to revisit. It's kind of a historical that we've done this, in that just dealing with data with different beams is really difficult. But with all of the work we've done on the LOFAR international stations, we have to do this anyway because the stations are even larger there. So we've kind of built up a bit more expertise on it, and maybe we're ready to revisit it. The difficulty comes kind of when you have sources that are just detected, for example, by the core stations and not detected by the remote stations and things like that. Another thing that affects the sensitivity is obviously the RFI environment. This is a ton of observations. In each observation is shown in, for example, if you just look at blue, is shown in a slightly different blue line. And you can see how much our fraction of how much data we have lost as a function of frequency. You can see at the very top of the band we use for LOTS, we almost lose all of the data. So that's why we cut off there. And we generally lose about 10% or 10 to 20% of data in an observation. Another thing that's started to affect our sensitivity quite a bit is confusion noise. So this is on the right, this is a deep image. I'll talk a little bit more about this image later. But basically, when we start going below about 50 microjansities per beam sensitivity, confusion starts to play a role and increases the noise quite a lot. And for example, on this plot on the left, if you just look at the vertical black curve, that's the sensitivity of this image on the right. And if you look at the just the yellow one, is probably the easiest. This shows the number of sources you have per PSF. So you're starting to get to just a few PSFs per source. So it's really getting very confusion limited. Because the LOFAR calibration is quite complicated, and because we have to kind of assume the ionosphere and other effects are constant over some patch, and we have to build up our own sky models of the sky, the dynamic range in LOFAR is sometimes not the best. This shows regions, just these are moderately bright sources, and you can see the artifacts introduced around them, and this is kind of over the whole survey, there's artifacts like this. We can characterize these, of course, and we can characterize them. So say each curve here is a different type of bright source, and you can see how much area it increases the noise around. And basically about 5% of the survey is really dynamic range limited. And for the deeper observations, it goes up to close to 10%. And then obviously you'd exclude those regions if you want to. Another thing that is quite complicated in LOTS is that we want to, for a lot of science cases, it seems that it's very necessary to determine what's a point source and what's an extended source. And this has proved really, really tricky in LOTS. So we think probably about 10% of the sources are extended. But the difficulty is identifying them. And that's because, well, for LOTS, it's very hard because for each observation, you have a different ionosphere, you have a different quality calibration, and the kind of separation between compact and extended sources is not, you can never really do it definitively anyway. Just to demonstrate that a little bit, this is some simple simulations. So the top is where, well, maybe ignore the top. If you, in the middle one is basically if you inject some sources into a image and recover those sources, this is the kind of distribution of peak over integrated flux density you get as a function of signal to noise. So the blue one is the idealized case, and the purple is what we actually see in LOTS. And some of this is because of extended sources, but a lot of it's just because sources are slightly blurred. Another aspect to this is that because we can't make the data infinitely large, we have to average the data a bit, and we average it in a way that causes some smearing. So far from the pointing center, sources get a little bit smeared. This is just an example of that. You can see for this particular field, both in the center, the ratio of total to peak flux is not 1, indicating everything is blurred. And then as you go further away from the field center, the blurring gets worse and worse. And in LOTS as well, when you mosaic this kind of effect together, it also has an impact. Now you can try your best to separate extended from sources from compact sources. For example, here in red is a distribution of all the sources in some LOTS area, and in blue is the distribution of ones that we think are compact, so kind of the most compact ones in the field. And you can say, where is the source more likely to come from kind of the tail of the red curve compared to the blue curve? And then you can kind of say when you think sources are extended, but you really get to define it yourself. And you can do that as a function of signal to noise, and you can make some kind of envelope like this, and you can try to separate the sources. But another effect that makes it even worse is that this all varies as a function of declination and observing conditions and everything like that. So another thing that's kind of plagued the LOFAR surveys for quite a while is the flux density scale. Now, we believe that the LOFAR HBA beams are basically really complicated, and the distant side lobes of the beams are very hard to get in the models accurately. So essentially what happens is if you, for example, take loads of observations of calibrators over the sky and try to calibrate them all with one of the calibrators and see what flux density you recover, you can't really get that better than about 10% at the moment in accuracy, which is a shame. So this is something we're going to try to revisit with a new observing campaign. But we think it's because of the LOFAR beam, so it's very hard to improve the models of that. So presently in LOTS, we basically scale every single LOTS pointing to try to improve the flux density scale, and we scale things. This is just our scaling factors for the LOTS fields processed so far, and you can see we're scaling some fields by as much as 40% to try to get the flux density better. And even after all of this scaling, it's a bit hard to see this one, but maybe the bottom left one shows it better. This is basically if you take overlapping sources in one pointing to another pointing and compare the flux densities, you find that sources in the north of a pointing are systematically brighter than sources in the south of a pointing. So it's not like we even have one flux density scale error over a single field. It's more complicated than that, and it changes across the field. So it's been proved hard for us to get better. And another aspect that makes it difficult as well is say this is, for example, a deep LOTS observation where we've observed a field lots of times. On the right here, you can see a histogram of all of the flux density ratios between peak and integrated flux. And you can see that none of these histograms are the same, and there's about a 5% typical difference between them. Another aspect that's difficult with LOTS is the astrometry. So because we calibrate each facet separately, the astrometry in theory can drift between facets. So what we do is we cross-match all of our facets, all of the sources in each facet with pan-stars or an optical survey, and we try to correct our astrometry so that it's good. We can typically apply like maybe an arc-second correction or something. But after we do this, we're able to get very good astrometry down to about 2.2 arc seconds, which is quite good considering our resolution is 6 arc seconds. Maybe I'll move on a little bit. I'll just summarize these things as I'm going through because I've got a bit more I wanted to mention. Another aspect that's very difficult is that we want to derive spectral indexes of sources. And LOFAR has, in the LOFAR surveys, we have about 120 to 170 megahertz frequency coverage. But with all the errors and things in amplitudes that we have, we believe we can get them down to about an accuracy of about 5% across the bandpass in what we know the flux density as. But doing it, having just this accuracy, it means you can't really derive a spectral index that's brighter, that's more accurate than 0.3. And that's 1 sigma, and that's even for an infinitely bright source. And it means that really you can't trust the in-band spectral index very much at all. This is just an example kind of showing that. You can see, for example, when you compare LOTS to NVSS and LOTS in-band, which is the one on the x-axis, and NVSS is on the right, you do get some kind of agreement, but there's just a huge error on it. And I think I kind of summarize is that this basically means you can detect extreme sources, but not a lot else. I'll miss this because it goes a little bit complicated. Well, I can not a bit complicated. It's a bit lengthy. But basically, I'll try to describe it. So so we want to know the completeness of LOTS, and this is another thing that's really hard. And this is because we calibrate the data lots and lots. So normally to assess the completeness of a survey or something, you inject sources into an image and see whether you detect those sources again and say how many you detect as a function of signal to noise or something. Now we can do that in lots, and you get there the solid curves here. So just look at the red, for example, you can see, or look at the blue, maybe that's easier. The blue just gives the fraction of sources detected at some flux density limit. And this is just if we inject them into the image. But as I said, LOFAR data is super manipulated in how much is processed. And if we do the same type of experiment, but inject them into uncalibrated data and then run the data through our pipeline, we get the dashed line instead. So you can see our completeness changes quite a lot depending on how we define it. Obviously, the one where we inject it into the image we inject it into the data is more accurate. But we can do the same for extended sources as well, but this gets even more complicated. And basically, if you kind of the summary of this one is that if you inject this blue thing into your data, these blue curves into your data, and then you try calibrating your data against your model, you recover the red. And this is because it's very hard to get the diffuse emission into the model. So it's quite often not in the calibration model and gets absorbed slightly. So diffuse emission in LOFAR is one of our most powerful things, but it's also really complicated in that you both have the cleaning effects I talked about earlier, the deconvolution ones, and then you have these absorption of emission that's not modeled effects that can cause another factor of 2 difference. This is just kind of a visual example of it. This is the injected image in the left, and this is actually what's recovered by the pipeline afterwards, if the source is not modeled. If it gets into the model, you can recover all of the flux. So, yeah. Another thing that we have in LoTSS is that we try to really accurately do the polarization. So during our calibration, we make the assumption that Q, U, and V are all equal to 0. And this works really well in that we get very, very good leakages. So this is, for example, on the right is without doing this calibration, and the left is after we do it. This is a Stokes V image. And we can calculate our leakage to about 0.06% or something for Stokes V. But it does have the effect of if you have a genuinely polarized source, for example, this bright source in the center here has 20 millijansky polarized emission. And because we've made this assumption that there's no polarized emission, we produce all of these spuriously polarized sources. And this is really hard for us to fix as well, because the only way we can really do it is either removing the polarized sources from the data or including them in our sky model. But both aspects are hard because we don't know what the polarized sky is like beforehand. This is just an image showing the differences in ionosphere between different observations, which is another thing we have to deal with. You can see that here some observations are really good quality and some are very poor quality. This is the same data, but just showing where they show the noise. Just look at either the red or the green, they're both fine. You can see that we're experiencing really different levels of image quality over an observation. We've got several types of unknown artifacts that appear in our data that we don't quite know the origin of. So for example, back 10 years ago now, we found these weird artifacts that occurred in the PSF of our images due to flagging of the data. And we've now found similar artifacts again in some images, but we don't know what causes them. We don't believe it's flagging anymore. We also have these types of artifacts you can see here around all brightish compact sources. There's negative holes, and we believe this is caused by removal of sources outside the field of view. We also have like sometimes the calibration fails, and sometimes it's really obvious that when it fails. I'll show you an example of that in a minute, but sometimes it's quite subtle. Like for example, in some of these images, it's a little bit subtle whether the calibration's failed or not. Like you can detect some sources in a particular facet, but not all the sources probably. So that's quite hard to characterize and account for. This is a more obvious case where the calibrations diverged, and this was because we're trying to image the galaxy. And after quite a lot of manual work, we managed to take that image to this. So we are able to improve things when we identify they're wrong, but it's quite time-consuming and hard. Another thing just to highlight is that we've tried a lot on LOTS DR3 to improve the data. We did pause for about 6 months before starting processing to try to improve the data. But basically, all we were able to do is take the image on the left, which is our LOTS DR2 image, and make this image on the right, which is kind of our best calibration strategy that we managed to devise so far. And the differences are so small that's why we decided not to reprocess most of LOTS DR2 and just to keep the data. I'll just talk about a few upcoming things. So we have the LOFAR Weave survey coming up soon, which is going to get spectra for 1 million LOFAR sources, and we will produce catalogs with spectroscopic redshifts and source classifications and things for many sources in LOTS. This shows an area that we're covering. Basically, the wide area covers LOTS, the extragalactic LOTS, and then we've got some deep regions that correspond to the LOTS deep fields. But we won't obviously get spectra for all LOTS sources. We'll have about 15 million radio sources and just 1 million cross matches. And I think I'll just have one more slide or a couple more slides. We're also working on releasing our deepest images to date. This is a 505-hour image of the Elias N1 field. There's some statistics about it here, but just it basically involved processing 300 terabytes of data that were accumulated over 7 years. But we detect a ton of sources. We detect nearly 150,000 sources in 24 square degrees. This is some images of it. Yeah. It's very, I won't go into details, very confusion limited. We detect lots of variable sources. These are a few examples of variable sources. A few more examples. We detect some nice Stokes V sources. We detect some stars and a pulsar in Stokes V. We believe we detect the galaxy. We're not quite managed to interpret this yet, but we think we're detecting the galaxy. There's lots of other studies to do polarization studies, to look at the really low resolution stuff, and to look at the field at high resolution. So this image in the bottom left shows the same image at 0.3 arcsecond to 6 arcsecond. All the data exists for that. And finally, after LOTS, we're making plans already. LOFAR is being upgraded to LOFAR 2. This basically means that LOFAR is going to become twice as powerful, essentially. So you can observe with, instead of 96 megahertz together, you can observe with twice that. And you can observe either with all of the bandwidth in the LBA or all in the HBA or split between the two. And another upgrade is that all of the LBA stations can now be used rather than LOFAR 1 actually just used half of the LBA. So this will make LOFAR a more competitive instrument as we go into the era of something like the SKA. It's basically a very different instrument from SKA low. It's going to be lower resolution, much higher resolution, much higher resolution and much lower frequency, but obviously it won't have a competitive sensitivity with the SKA. It's going to do lots of science in different areas. And what we're proposing with LOTS, I'll just summarize, is we're proposing, this is LOTS image on the left. And what we're proposing to do to LOTS is to take the whole sky from the image on the left to the image on the right. So this is our 6 arcsecond resolution image on the left. And this is a 0.3 arcsecond counterpart using the same data. And we can't quite do this over the whole sky at the moment. But we're going to basically put a pointing between every existing LOTS pointing. And then we'll hopefully get loads and loads of images that look like this over the whole sky. And improve the sensitivity as well by a factor of 3 at the same time. We're also proposing very deep observations up to 2,000 hours in a single field. So sorry, I probably went a bit over time and was a bit rushed at the end. But that last bit I think is quite exciting in that we want to do this very high resolution imaging, but the computational cost at the moment is in the billions of core hours. So we need a lot of development to actually make it feasible. Thanks, I'll leave it there, Rita.
Yeah, thank you. So questions. So I'll request anyone with a question to unmute and ask.
Oh, hello. Hello.
Yes,
Hello.
Ramanand, go ahead.
Yeah. Hi. Thanks for the nice talk. So, can you just go back to the DD facet slide where you just explaining the DD facet and KMS thing? So, I have a question that how the facets are created. I mean, it is just like you just have a, let's say, 10 bright sources in the field of view and you create 10 facets, or can you just briefly mention? Yeah. How the
Yeah,
facet.
so we kind of so we decide on a number of facets, that's an input parameter, and then
Okay.
we give it kind of our current model of the field that
Okay.
we've derived from a direction independent image, and it basically tries to get kind of roughly uniform flux density in each facet, and then it does a tessellation of the sky. Yeah, so normally the facets are quite, well, they're normally smaller, for example, around bright sources, and they're bigger kind of on the outskirts of the field where the primary beam attenuation is quite large.
Okay, and how the size of the facets will affect the computational speed on the calibration and all these things?
Ooh, yeah, good question. I don't know exactly the scaling.
Okay,
No, I don't know the scaling. I don't think it's like linear or anything. Um, well, some aspects are linear, but not all of it. I don't know how the complete pipeline would change. But we can, for example, run with, say, 100 facets,
uh,
and then you generally improve the image quality quite a lot, but you have the problem of more absorption of diffuse emission and things like that. So 45 was really a compromise, and not because of compute time, more for stability. You have less stability if you have more facets too. But yeah, there's something that it could be better, much better optimized.
so I have another question. Can I go ahead? Yeah.
Yeah, anyone
Yeah.
else having a question, please raise your hand. Yeah, go ahead, Ramanand.
Yeah. So can you just go back to the slides where you were mentioning that you have a multiplied the scaling factor to match the flux calculation of the LOFAR? Can you
Yeah.
just explain a bit? Maybe I have just missed. Yeah. So
How we do it?
yeah, I mean scaling
Yeah.
factor.
Yeah, so ideally you would know the flux density of a source
Yeah.
at 150 megahertz. The only issue is that we don't really. So for example, we have TGSS,
Yeah.
but we more use TGSS as a cross match afterwards
Mm-hmm.
to see how well we've done. What we actually do is we cross match all of our sources to NVSS, which obviously has quite a reliable flux density scale. And then we assume that every field has the same typical spectral index between LOTS and NVSS. And we scale our fields so that that's the case.
Okay.
Yeah, so it's
Thank you.
actually tied to 1.4 gigahertz. Yeah.
Thank you.
Yeah, I don't see a raised hand, but please unmute and ask your question, please. Okay, I have one question, team. So having, the experience of lots, what do you think would be, one of the major lessons for any future survey with, SKA like instrument?
Oh, yeah, I don't know really. I mean, I think you really need some very dedicated people who are going to work on it for a long time, who aren't going to kind of move on to the next right thing that comes along. But that's very important. Things like stable software and people who have developed a very good software, maybe like kind of being open to different techniques. So not putting all your eggs in one basket and saying this is the way we're going to process the data, but being open to new people coming along with new ideas for processing it and just kind of accepting what's best. Yeah, and then just a lot of work for a long period of time, I think. And then just trying your best to make it as good as possible. So with all the characterization and things like that, and making sure that you produce products that satisfy what the users want, so that people can do science. Because I think the most important output is obviously how much science you can facilitate and how good that science is.
Yeah, thank you. Anyone else, please unmute and ask your question. Um, so one question regarding the LOFA international um, baselines. So over there, because at those frequencies we really have not seen the sky at all. How is the you know like for self calibration? So essentially, one would rely on self calibration like process to recover the sources. Um, so
Yeah,
how
yeah.
much is the challenge, and what is
It's
done to
very
get?
hard. Yeah, so basically only about 15% of the sources survive at that resolution compared to 6 arc seconds, as you can kind of see from this map. Many of the things that are detected at 6 arc seconds aren't detectable at 0.3. And for the calibration, you need to ensure there's enough compact flux on the longest baselines to be able to calibrate. And this is one of the big issues. Basically, there's ways like we do have the long baseline calibrator survey. There's also ways you can try to deduce already from the visibilities what's compact. And another way is you simply make a list of kind of candidates and go through and see and actually analyze the data on the fly to see what's compact. Yeah, but that's one of the difficult parts. Yeah.
Yeah, maybe maybe we if we if do you have 1 or 2 minutes, we could. Um, is there any other question? Please go ahead and ask. Okay. Okay. If not, then thank you for a great talk, and we look forward to the next data release of LOTS.
Thank you very much. Yeah, and if anyone wants to use LOTS before it's released, do get in touch and see what we can do. Thank you.
Yeah. Yeah. Thank you very much for your time, and thank you for all of you to attend. See you at the next RATeS seminar.
Bye.
Bye.